Using average rate of change to help us understand function behavior. You may recall from class, we studied this particular function, which had that funny number e in it. Regardless, this function described how people get sick over time. To be able to come up with a decent graph requires some work, but I've done that for us. We could talk about 45 days of the representing the spread of the flu, and we could talk about a population that seems to be 800, so that's probably the size of the school. And once everybody in the school has had the flu, then the epidemic stops. So when you look at the graph in more detail, you can look at average rates of change periodically throughout this course of this spread of the flu. So for example, in the first 10 days, we have the steepness of the red line showing us that there is a slow rate of increase in the beginning of the epidemic, and the steeper line in the middle shows a rapid rate of increase during the middle part of the epidemic, and at the end, the last many days of the epidemic, the rate of increase of people getting sick was much, much smaller. I can tell all of this just by looking at the steepness of the lines. Steep lines mean rapid change, and flat lines mean slower change, relatively speaking. Using a table of values, I was able to calculate various change rates at various moments along the span of the epidemic. In the first 10 days, we have 9 students per day getting sick, which is enough. But as you can see from day 15 to day 25, we have about 37 students per day getting sick, which is much more rapid, as reflected by this middle portion, the steeper line. And finally, in the last 10 days that I used that I used for the graph, I found about 3 students per day were getting sick. So what we need to do is we need to take our understanding of the graph, we need to take our understanding of how flu spreads, we need to take our average rates of change as shown, and put it all together to make a decent and concise description of the function. So we start with an as a function of statement. The number of people infected with the flu is a function of time and days. That's chapter 1. The number of people getting the flu increases at an increasing rate at first, about 9 students over the first per day over the first 10 days. The daily infection rate increases until about the 25th day, and it's about 37 students per day from 15 to 25 days. By the end of the first month, the number of infections is still increasing, but at a much slower rate. That's about 3 students per day from 35 to 45 days. So what you can see is I included a variable relationship, and then I talk about the flu is increasing, and then I talk about how fast the flu is increasing using some specific examples from average rate of change. So that's what we talked about in class. One of the first homework assignments I gave was using this function, which gives the pressure of the atmosphere as a function of height in miles. Now, wanted to talk briefly about how to get the graph of that equation into the calculator. I mean, the entering the equation into the calculator is the easy part. It's how do we get a decent viewing window that matters. So I have to go back to the equation and see that h represents miles of altitude, and we're talking about atmospheric pressure, so I should know something about how thick the atmosphere is. Thank you, Google. Here we can see, if I can scroll this over, well, unfortunately I have the wrong size window for you to see this. Let me, oh yeah, let's move this over just a little bit. There we go. So I asked Google, I said, hi Google, well, how thick is the Earth's atmosphere? And here it says the Earth's atmosphere is about 300 miles thick, but most of the atmosphere is within 10 miles. So this is the part that helps me determine what I should set for a viewing window on the calculator. That is to say, since most of the atmosphere is in the first 10 miles, then I'm just going to go from 0 to 10 to get my window for the x's. Every mile I'll put a little tick mark. And then I can go to my table, start at 0, go up by 1 mile at a time, and automatically give me a list of altitudes. So I look at the table, I can see that altitudes start at 14.7 psi and they decrease from there, which is logical. We should expect atmospheric pressure to go down. So look at the graph, and it shows what I expected would happen. So anyway, now that I've used all my resources to get a reasonable graph of atmospheric pressure as a function of height in miles, I have to go about the task of describing that function. So here's the graph again as we've seen it, and here I actually make a couple of calculations. From 0 to 2 miles, I find the average rate of change, and I find that I lost about 2 psi, pounds per square inch, every mile I increased in the first 2 miles. But from 8 to 10 miles, I lost about a half a pound per square inch for each mile increase from 8 to 10 miles. So I put the graph, which has a nice viewing window. I put the average change rates that I calculated. I put all of this information together to create the following description. Atmospheric pressure is a function of height above sea level. As your height increases, the pressure from atmosphere decreases at a decreasing rate. It's this phrase right here, decreases at a decreasing rate, that some people are able to say, but fewer people actually understand. So when I say something like the pressure decreases at a decreasing rate, I would like an example to follow to tell the reader that you understand what decreasing at a decreasing rate means. So, for example, I say from sea level to 2 miles in the atmosphere, there's a loss of over 2 psi for each mile increase, whereas from 10 or 8 to 10 miles, there's only about a half a psi, pound per square inch, loss for each mile. And I even give a possible reason: less atmosphere. So, that concludes a video on how to describe functions using average rate of change. You can use the other three examples to help reinforce what I've talked about here.